This is the final lesson of this week, and in this lesson we'll look at how we represent negative numbers in binary. In this lesson we'll look at different ways of making negative binary numbers and see how to create numbers using both of the two methods, which are called sign and magnitude and 2's complement. Sign and magnitude is an easier method, but the numbers can't be used in calculations. 2's complement numbers can be used in calculations, but it takes slightly more calculation to produce a 2's complement number. In sign and magnitude binary numbers, the first bit of the number, the one on the far left, shows the sign. 1 represents minus and 0 represents plus. So get that the right way around, 0 for plus and 1 for minus. The next 7 bits show the magnitude, that means how big the number is. So sign and magnitude. Here's an example. A binary number is represented as 10010001 using sign and magnitude. What is the value of the number? Well, the first bit, the 1, represents minus. Remember, 1 is minus. And the rest of the number represents 17. It's a 16 and a 1. So the answer is minus 17. Or let's say we had to do an example in the opposite direction to represent the value minus 70 in binary using sign and magnitude. First of all, we can represent the sign minus using the bit 1 for the first bit, and then we can represent the number 70 as 64 plus 4 plus 2, and we write those bits in. So the answer is 11000110. So sign and magnitude is quite an easy method to use. So here's a very short test. Can you represent these 3 numbers, decimal numbers, minus 10, minus 80 and minus 111 using the sign and magnitude system? I'm going to give you a chance now, so pause the video. Quickly write down your answers to these questions and I'll show the answers on the next slide. So here are the answers. You'll see because they're all minus numbers, they all begin with the number 1 and the remaining 7 bits represent the magnitude. 2's complement is a different way of representing negative numbers in binary. In the exam, they'll tell you which method to use if they ask you to represent a binary number. But if you need to use a negative number in any kind of calculation, you should always use 2's complement. The position on the left of a binary number has the largest position value. It's sometimes called the most significant bit. In a byte, the most significant bit has the value 128. In 2's complement, the most significant bit is given a negative value. So in this case, it would be minus 128. In order to convert a 2's complement number into decimal, you create the position bit with the most significant bit having a negative value. You then put the binary digits into the position grid and you add the values together in the usual way. So in this case, minus 128 plus 16 plus 8 makes minus 104. So this pattern of bits represents minus 104. Here's another worked example. Put the bits into the grid and add them together. Minus 128 plus 32 is minus 96. So it's as simple as that. So here's a test. Here are some binary numbers represented using 2's complement. All but the first are negative numbers. So see if you can convert all of those into their decimal equivalent. Pause the video now, do these conversions to check that you know how to do it. It's really important you know how to do this before we go on to the next topic. So pause the video, write in your answers, and in a moment I'll show you the right answers. So here are the answers. As you can see, a 2's complement number that begins with 0 is always a positive number, but if it begins with a 1, it's always a negative number. In any 2's complement number, a number that's composed entirely of 1's always represents -1. So if we're using 2's complement, the largest positive value we can represent in 1 byte is 127. The smallest of positive value is 1. 0 is all noughts, -1 is all ones, and the largest negative value we can represent is -128. So to recap, in this lesson you've learnt about the 2 ways of making binary numbers. You've learned how to convert between decimal and sign and magnitude numbers and vice versa. We've also seen how we can convert a 2's complement number to decimal, but I haven't talked so much about converting decimal to 2's complement. There's a shortcut method of doing this, but I'm going to show you that next week. So your task this week is to revise everything that we have learned, ready for the test in a couple of weeks' time. So it's really important because particularly understanding binary addition and 2's complement will set you the foundation for what we're going to be doing for several weeks to come. So don't skimp this. Okay, so I'll see you next week where we'll do some more work with binary numbers. Bye for now.